Welcome to qnawire.
In this problem, we have a closed feedwater heater in our turbine. So we have an ideal Rankine cycle here. So we have isentropic turbine and pump. Let's see here. We have we have our in this case we have this bleed steam coming off here, heating up the feed water here, going into the boiler. And then it basically then comes out as a saturated liquid here. Pressure is throttled down and then sent back to the condenser at 8. So we have, looking at the flow here, we have from the pump going into the feed water heater, getting the temperature raised up, and then getting into the boiler, and then boiling, getting into the superheated region, going through the turbine. We bleed some off there. The rest of it goes through. The bleed comes over to, let's see here. The bleed goes to over to 7 here, from 5 to 7, and then it's throttled back down to this, the pressure of the condenser. Well, this comes out of the end of the turbine, and then we get these mixed back here in the condenser, and then we go back onto the pump and repeat the cycle. So high pressure side is 3 megapascals, low pressure side down here is 20 kilopascals. The bleed pressure is 1 megapascal, and the temperature at the turbine inlet is 350 degrees C. Because everything is isentropic, we have these relationships, and then we have saturated liquid at 7. So we can get saturated liquid at 1 also. So we can get enthalpy and specific volume at 1, so we can get the power into the pump. And then that allows us to find the enthalpy at 2. The enthalpy at 4 and the entropy at 4 we can get because we have the pressure and temperature there. At 5, we can get the enthalpy because we have the pressure and the entropy now. It's the same as here. So this equals S5 and equals S6. And then we have at 6 then, and it looks like I drew this a little wrong because this should be outside. I think this is a superheated value. So this should actually come in like this. Anyway, so this should be not in the two-phase region. Let's see here. Then we have the quality factor at 6 is about 83.6%. So then we get the enthalpy at 6. The enthalpy at 7 we can get because we know the temperature at 7, and we know that it is saturated liquid. And then we know that the enthalpy at 8 is the same because we're just going through a throttling process that we're assuming to be perfectly efficient. And then finally, we can get the enthalpy at 3 because we know the temperature at 3 now, and we also know the pressure at 3. So if we do a control volume around the feed water heater, here's conservation of energy. I have also conservation of mass says that m dot 7 equals m dot 5 and m dot 3 equals m dot 2. So here we have the enthalpy flowing in and the enthalpy flowing out. And let's see here, we then have dividing through by m dot 4 and using the mass conservation relationships and knowing that m dot 4 is the same as m dot 3 and m dot 2. We then know that we have this relationship for y, which is m dot 5 over m dot 4. So that is the percentage of bleed that we bled off the turbine as a percentage of the inlet. Get that. So we know all the enthalpies here, so we can find y, and that's about 24.4%. So we're taking about 24.4% by mass of the steam out here. Now we can get the work from the turbine. So the work in the first stage here, going from here to here, and then the work after we bled some off. So again, we got to reduce the amount of steam that is going through there. So the specific work of the turbine is about 741 kilojoules per kilogram. Now we can get the heat transfer in, which is just the heat transfer from difference in enthalpy from 4 to 3. We get this value, and then the net work in, we can take this and subtract the work that we had to put into the pump, this value, and then we wind up with an efficiency of about 31.4%.